In this video, we're going to talk about horizontal projectile motion. So things to remember that we talked about in class: air resistance is going to be ignored in these problems, and because of that, horizontal velocity is constant. That's going to be a key to these problems. Horizontal velocity is constant. We got to remember that. But vertical velocity is changing, or in other words, vertically the object will be accelerating due to gravity. And time is the same for both horizontal and vertical directions, and we'll explain what that means as we go through these example problems. Number one, it says a ball is moving horizontally at 3.8 meters per second when it leaves the edge of a 1.2 meter high table. How long does it take for the ball to hit the ground, and what is the horizontal range of the ball after it leaves the table? So let's go through this and kind of draw a picture of what's happening to this, to the motion of this ball. So it's going to go across the table, and then once it leaves the table, its motion will look something like this. And so after it leaves the table, it's going to be pulled down by the acceleration due to gravity. But it had a speed of 3.8 meters per second when it left the table, so it's going to continue that velocity as it goes horizontally, and then it's going to hit the ground somewhere over here. And if you draw a line straight down from this table, if you measure this distance here, this is called its range. Also horizontal displacement. And so that's what is going to be happening, and we're going to go through how to solve these types of problems. Okay, and so again, I think the best place to start is always to list what you know and what you don't know. But we noticed something about this problem that's a little different than what we've seen before. Is now, instead of just going up and down, the motion of this ball is in two dimensions. We have a left and right component, and we have a component that's up and down. So there's our two dimensions. And so I think what's crucial about these problems is to separate the components of motion. So we know there's horizontal motion, and we know there's vertical motion. And so I always separate those two and list your knowns and unknowns for both of them. So I'm going to switch colors and list my, I always like to start with the vertical, what I know is happening vertically. We know that as it leaves the table, that initial velocity is going to be 0. Now we're talking vertically now, so as the ball leaves the table, it's just like it was being dropped. Vertical initial velocity is going to be equal to 0 meters per second. Time initial, of course, is always the same. It's always 0 seconds. Displacement initial, that point at which it leaves the table, I'm going to call that point 0 as well. And now we know acceleration is going to be a negative 9.8 meters per second squared. Our velocity final, when it hits the ground, it doesn't tell us how fast the ball's moving, so I'm going to put a question mark. Time final, we don't know that either, so question mark. And displacement final, we do know. The table, it said, was 1.2 meters high, and so our displacement final, the ball, since the ball is going to be lower than its initial point, I'm going to say is a negative, so our displacement final is a negative 1.2 meters. 1.2 meters. Okay. And now that's everything vertically. Now let's list everything that we know horizontally. Horizontally, the initial velocity is, it said it left the table at 3.8 meters per second. So 3.8. And in fact, that's going to be our final velocity as well, because horizontal velocity is constant. So 3.8 for final velocity. Our time initial is equal to 0. Our time final, we don't know. Our, let me list displacement over here. Displacement initial is 0. That point at which it leaves the table is 0. And then it's going to move horizontally a certain amount of distance, or displacement. So displacement final, we don't know. Okay. And that's all of the variables that we do know from this problem. And so now the step goes to picking an equation that will help us. And one thing that I can tell you that makes a lot of sense is always solve for time vertically first. That will be your first step in these problems, is to solve for the time that the ball is in the air vertically. And so we're not going to use equation number 1 because that's for horizontal. Let me make a note of that. That's for horizontal motion. So vertically we can't solve for it. We're going to solve for time now vertically. And so we better make sure that the equation has time in it. There's time here and 2, and equation number 3 has time, and equation number 4 has time. Equation number 5 doesn't have time, so I'm going to eliminate that one as well. Okay. Now let's see if we can use equation number 2 to solve for time. We don't have time, but we don't have final velocity either. So we cannot use equation number 2. Equation number 3. We don't have final velocity and we don't have time, so we cannot use that one. Equation number 4, let's see if we can use that one. We do have displacement, we have an initial velocity, we don't have time, and we know acceleration and we don't have time. So there's only one variable that we don't know, so let's use equation number 4 to solve for time vertically. And so I'm going to do this part over here. So let me rewrite that equation. Displacement is equal to velocity initial times time plus 1/2 at squared. Now let's fill in the variables that we know. Our displacement final was a negative 1.2, so minus 1.2. And that's going to be equal to velocity initial vertically was 0. So I'm going to call that 0 and leave this term out. And so we're left with 1/2 times a, which is a negative 9.8 meters per second squared, times time. And we don't know time, but it's also squared. So now we can solve this equation. What I would do first is move times both sides by 2 to get this 2 to the other, and remove that 2. So negative 1.2 times 2. And then what I would do, so that gets rid of this 2, is divide both sides by a negative 9.8. So divide that by a negative 9.8. And what I get is 0.245 is equal to t squared. And now to get t by itself, the only way to remove this squared term is to square root each side. You take the square root of each side, and then you're left with just t. So let me take the square root of that. And my calculator says it's t is equal to 0.495. And that'll be, time is always measured in seconds, so that's seconds. So that's the time that this ball will be in the air. And now that we know the time and we solve for time, we can use the horizontal equation now to solve for horizontal displacement, or its range. And that is given by equation number 1. And so displacement is equal to the horizontal velocity times time. Horizontal velocity, it told us, was 3.8. So 3.8 times the time, which was 0.495 meters per second, and that will give us our displacement. So times 3.8, and my calculator tells me that the displacement of this ball horizontally will be 1.88 meters. And so that's the range, or how far horizontally this ball will land from where it left the table. So this range is equal to 1.88 meters. Okay, and that's how you would solve a problem like this. I think draw the picture, list your variables, and then pick your equations. Vertically, if you solve for that, solve for time vertically first, will help you solve your horizontal displacement. And so hopefully that helps. I've got one more example problem with horizontal projectile motion. It says if you drop a banana peel out the car window 1.4 meters above the ground while traveling down the road at 22 meters per second, how far horizontally from the initial dropping point will the peel hit the ground? So that's a lot of information. Let's draw a picture to help us visually see what's going on here. So we got a car. Okay, here's our car, and we're dropping a banana peel out the car window that is 1.4 meters above the ground. So this distance from where you drop it to the ground is 1.4 meters. Okay, and we also know that the car is going 22.0 meters per second down the road. So that's its horizontal velocity. All right, and we're going to set this problem up just like we did with the last problem, breaking the components of this banana peel's motion into its two dimensions. So we know there's a horizontal component, and there's going to be a vertical component. And now let's list all the variables that we know. Vertically, we were dropping it, so our initial velocity of that banana peel, vertically at least, was 0 meters per second. The final velocity, we don't know how fast it's going. It didn't tell us. Time initial is always 0, and time final, it didn't tell us. Displacement initial vertically, that point at which you release the banana peel, I'm going to call is 0. And then displacement final then is how far it moves down. And it told us that the displacement was 1.4 meters. But remember that banana peel is falling down, so I'm going to call that a negative 1.4 meters below where it started from. And we also know acceleration. I should always put acceleration is equal to a negative 9.8 meters per second squared. Okay, horizontally we know that the velocity is constant, so there's not going to be initial or final. And that was the speed of the car, which was 22.0 meters per second. We know, let's see, displacement is what it's asking us for. So we don't know horizontal displacement, and we don't know the time yet. And so just like in the last problem, we're going to use the first step is to solve for time, but we're going to do that vertically. So we can't use equation number 1. Again, we're going to come down and use equation number 4 and solve for time vertically. If I, let's throw this equation up over here. Let's see. So displacement is equal to velocity initial. I'm just rewriting equation number 4 times time plus 1/2 at squared. Our displacement was negative 1.4, so minus 1.4 is equal to our initial velocity vertically was 0, so I'm going to keep that 0, and so leave that term out. We got 1/2 times negative 9.8 times time squared. And now we can solve for time. Let's see, a negative 1.4, I'm going to times each side by 2, so times by 2, and then divide each side by a negative 9.8. And I'm getting that, and so what I'm finding is t squared is equal to 0.286. Take the square root of both sides to get t by itself. And so a square root of 0.286. And so time that banana peel is in the air is going to be equal to 0.5 0.35 seconds. So that's the time that the banana peel is in the air. Now that we have that, we can solve for the horizontal displacement of the banana peel. So you're going to release it there. The car is still going. It's going to land while the car is somewhere over here. And so using equation number 1, displacement is equal to velocity times time. The velocity was 22.0 meters per second. Timesing it by the time that we just found, 0.535. And so times by 22. I'm finding that the banana peel has the range of 11.8 meters. And so if we think about what this means, if you drop the banana peel while you're going 22 meters per second, your car is going to move 11.8 meters before that banana peel hits the ground. And so hopefully that helps. I've got a couple of video physics questions for you that I'll show you now. So I'll scroll through them slowly. Again, there's 2 questions, very similar to the ones we just solved. So if you get confused, go back in the video, watch it. If you still can't figure out and you're still having problems, come talk to me and I will help you figure it out together. So good luck.